last one, we were talking about, we did an alternating current. Remember, we had a waveform that was kind of sinusoidal, okay? In this one, we're going to look at a slightly different arrangement of ends A and D, all right? Remember, A, AB, and C to D. So I call that end A and end D, okay? Now, what we had in the last one, we had our north and our south. Now, let's just change something, all right? Let's just change something. Let's once again keep this over here, north and south, all right? Like that. So magnetic flux, same as I've got here on the table. Now I'm going to have the same coil going through here, all right? And I'm going to have the same A, B, C to D. I'm only going to now look at the ends. Okay? The previous ends, remember, they came through and it was connected to a ring here and a ring at the back that then turned, right? And we had our brushes attached to each. And we found that the charge on end A went from positive to negative as we turned. So brush A became positive and then negative. Now I'm going to change it and I'm going to have end A, okay, end A, whoops, sorry. I know you guys have got this in your textbooks anyway, and this is not to scale. You've got something that looks like a C, like that. Okay, they are not connected. It goes back like that. It's a three-dimensional thing, all right? This is brush A, and this is brush, I'm not going to call it B, I'm going to call it brush D, okay? Because now what I've got, these two ends here, all right, A comes along there, all right, and D is there, right? So this thing is, in essence, there's a ring over this, but the ring is split, right? So this is going to touch and then go on to the next one, right? Just think about these two ends turning inside this ring. There we go, there's the ring. Now they are turning inside there, right? But the rings are not connected, it's two halves. So what we're saying is that for part of the movement, you can see A is going to be connected to A. And then A is going to connect to D, all right? So let's just, so that we don't get confused, let's call this one, okay? If you don't mind, I want to call that brush number 1 and brush number 2, okay? I just don't want to confuse the issue of the A's and the B's, the C's and the D's. Now, let's have a look what happens, right? We use Fleming's right-hand dynamo rule. So we say, right, guys, what are we doing? We are moving this one up, this one down. We only look at AB, okay? We look at AB, right? Remember, this is our thing out here, right? Okay, we look at AB. AB is going up. Here it is. AB is going up. It's cut maximum at this point. Current is going that way. So A is going to be positive, right? Let's put A in as positive, okay? Okay. A is positive because my current is moving that way, right? Now as it moves, let's draw just one below, all right? I'm trying on the fly as we go with this because, you know, it's not the easiest thing to actually draw in 3D. All right, just pretend we've got, now, all right, there's our split ring, okay? I know, it's not great. But now A has moved up to the middle. End A is there and end D because we are turning that way, right? We are going that way. Can you see now, end A is over here, and right at this point, there's no current, right? Because the normal is at 0. Maximum flux, no current. Okie dokes? Now what are we going to do? Next we're saying, all right then, what do I do now? Now I turn it further. So let me just move it down a wee bit. All right? Okay. put in my split ring. Okay, and this is brush 1, brush 2, brush 1, brush 2. Now, remember, now D is over here and A is there. All right, there's the going up to the loop there. So now I've got A, this piece is going down through the field. All right, so let's see. Okay, field, down, current coming that way. All right, so A is negative. So let's put it in. This is negative and D is positive. So what does that mean? Can you see? Look at this. What does it mean for these brushes? When A is touching brush 1, here, A is here, but remember it's this, huh? A is touching that brush at this point. It's moving up in the field, which means the electrons are going away from it. It's leaving it as positive. So brush 1 is positive. Okay? Brush 1 is positive, which means brush 2 must be negative. As it moves through that point, through the middle of the split ring is there and there, okay? As it moves through there, there's no current. It's not touching anywhere, doesn't have to. In fact, it's insulated from each other, the two split rings. It shouldn't touch. Why? Because otherwise it's not going to work. So as it's moving, remember you are forcing it round, huh? So you're still going to keep moving it. It's in no man's land. So it's basically no EMF, no current. We are not cutting flux. There, are we? We're not cutting the flux line. Now as I move it down, all right, can you see this end is now touching the other brush? It's touching brush 2. But as it moves down, okay, brush 2 is getting all the electrons, which means that brush 2 stays negative, and brush 1 stays positive. Okay, it's as simple as that, all right? So now we've got a different scenario. I always forget to do that. My bad, sorry. So and we've got a different scenario now. What we've got here is we've got also generating a flow of current. If we look at the graph, let's have a look at the graph, all right, of what it looks like. Right? And once again, come on, here we go. Okay, now we say, all right, let's go 0, because we know how this works. 0, 90, 180 degrees, 270 degrees, and 360. That is the normal, right? So at 0 degrees, I have got 0 because I am here. All right? And as I move, remember, so I go up over there. Okay. For you purists amongst us, I'm going to go like that. Now, remember last time it changed. But on this one, just hold on, brush 1 stays positive. Right? So it was positive moving up to 180. And what happens now? It stays positive. So yes, it does this. Because brush 1 stays positive, okay? This could be the current, this could be, or the EMF. Once again, I know I'm going to do it because the voltage is different, okay? And the voltage will go just the same as the other one, right? You can remember that graph, what it looks like. The difference here is the previous one went negative, this one doesn't. This one is called, I want to do it in my normal printing. This one is our direct current. All right, aka DC. Okay, some countries use AC, which is the previous one. Some countries use DC. Now, this character, all right, the direct current, Okay, we have got, just make checking, all right. What we've got here, the direct current, this is produced by a dynamo. Okay, direct current produced by a dynamo. So all we've got here, okay, is we now need to look and see what actually are we doing. Common to both is spinning a coil in a magnetic field. Please note, magnetic field could be there, coil could be this way, coil could be that way. What are the steps that we do? Okay, I'm going to get to those. But in essence, what's it about? It's about how we brush off the electrons at A and D, isn't it? If we're using the slip ring, A and D are going to change because this starts off as positive, and when I cut that way, the current's flowing this way, so it becomes negative. The current alternates, changes from a plus to a minus. Changes direction, that's what's happening. The voltage does the same. Okay? Now, if we do it and we've got what we're describing here, the commutator, all right, the split ring, obviously because it's got a split down the middle, all right, let's put it in green, all right, anything to help. It is split. Can you see? It's two separate steel C's, two separate steel half tubes. Probably copper actually, although probably steel because of wearing. So as the thing is turning, it's coming into contact with these guys, and it's actually changing brush 2. Right? You could change if you like, you can turn all of it, but just let's keep it as it is and say it's the ends. We're looking at what's happening at the ends. Oh, by the way, before I forget, please know how to draw and label all of this. Favorite question is you have got a generator, label the parts of the generator and show the waveform and explain how the waveform exists. In other words, generator, you say, hang on, generator, alternating current. Alternating current is the slip ring, and you work backwards from there, right? It's not difficult. I know everybody says I say that a lot, but it's not, right? It's quite an easy, cool section to deal with. You just got to remember that. Then we say to ourselves, right, know the parts of the dynamo, which has got the split ring. That one generates a waveform that looks like that. Now, let's just have a look at something over here. I just want to move this up slightly and add another page into it. What have we got here? We've said, okay, we've got this. Now, let's just look at a problem, shall we? All right. Let us say I have got a field that looks, okay, something like this, black. We've got a field and they've drawn it like this. All right. They've drawn, it could be Earth's magnetic field, and you've got a wire AB which moves that way through the field. Which way does the current flow? You go, first of all, I am moving it. Therefore, I am applying an external force, right hand. Okay? We're going to get to the left hand soon. But it's a right hand because I'm applying an external force, and this is the direction, also known as M for movement, okay, which is then our thumb. So I say right. Field, what does those little plus signs or arrows mean? Usually, I've very often drawn like an arrow. Sorry, I drew it as a plus. I shouldn't have, okay? So what have I got here now? I'm changing these to crosses, all right, like that. It means that the field is going into the paper. If the field is going in, this is my forefinger is my field, the thumb is the movement, so the current is going to be going from A down to B, right? It's not, remember, you just got to look for the direction of the field first, right? Now, let's go back to this one. Okay, all right. Know how to draw it. All right, so what we got is that. Let's just see, okay, how do we manage questions, okay? If these are connected, normally we're going to be connecting it to a circuit, obviously, because we're using it, okay? And they'll want to know which way is the current going to flow, etc., etc. Okay, step 1. All right, this is what you do. Step 1, all right, draw in the magnetic lines. Draw in magnetic flux lines from north to south, all right? If they've given you the lines, label north-south, okay? This gives the direction, okay? Step 2, this gives the forefinger, aka field direction, right? Step 2, examine the arrangement. Let's make a note of this. Examine the given arrangement at the ends. Is it a slip or a split ring? Okay, so there's a decision you're going to go through, all right? If it's a slip ring, straight away the slip ring generates AC, so we've got that, okay? If it's a split ring, it generates DC, which is this guy, all right? Generating DC, and we're calling it a dynamo, and this one we call a generator. Right? Simple as that. So that's what we do. We say, okay, then we say, all right, next step, all right, is I've got here as step 3, pick one side of loop, okay, and work out what's missing. Why do I say that? Hang on. I've got forefinger field. I've got thumb motion, movement, direction. And I've got second, which is current. There will always be 2 out of 3. They will either tell you that in a generator or in a dynamo, all right, the current is flowing this way, or this is the graph, or whatever. They will tell you maybe which way the current is flowing, all right? So they'll say this side is always positive, then you can work it out. But you'll be given the current direction. And they will give you the direction maybe that it moves, and then you can work out which way the field goes, right? If it's moving up, current going that way, moving up, you know, north to south, right? Always 2 out of the 3 will be given. You can't solve it if they're not, okay? Now, all right, when we solve these problems, that's what we look for. We go to it and we say, right, we first of all identify from the ends, what is it? Is it AC or DC? That'll tell us which waveform comes out, okay? It tells us if it's going to reverse, okay? It answers a whole host of questions. The only other thing you have to do is use your right hand and identify 2 out of the 3 that you are given. It could be this way, but the same applies, right? It could be north at the bottom and south at the top, and this spinning that way. You have got 2 out of the 3 always in every single problem that you will encounter in these. Okay? All right. So, if they've given you the current, for example, okay, you can allocate a plus or a minus to the brush side. Let's just say, all right, let's just go back up here. Let's say, for example, they've given us current. All right. Let's say current given. All right. You will go and you'll look, the current is given, so therefore find the plus and the minus brush. Right? And you can answer the questions from that. So 2 out of the 3 will always be given to you. All right? Lastly, I want to just go through something very quickly. Remember, if they give us something, say like that, okay, just for argument's sake, they give us this, and they say that's the EMF. First of all, we say plus, minus, therefore that's AC, so it must have had slip ring, okay? Oh, question, how do I change an AC to a DC? Change the commutator from a slip to a split, or vice versa. Classic question again. So I've got the EMF and I've got a minus EMF there. Immediately, because I've got the shape, I've got that, right? Now look, it is starting at a plus value and going to 0. So essentially, when they have started this, how did they start it? They started it there, right? They had to, right? Just look at it. They had to start it here because they started at a max. Because they started at a maximum value, the loop must have been there. So therefore they started there and were moving it that way around, right? All they've done is they've said, instead, I'm going to be starting at 90 degrees, 180, 270 degrees, 360, and, 92, 3, and that's going to be now at 0 degrees, isn't it? 90, 180, 270, 360, and back up at 0, right? So that's one revolution, okay? Sorry, 90, my bad. Sorry. What we're saying is it started at 90, it's ending at 90, so it's starting here and going around like that, right? And there it stops. So yes, they can start this off at anywhere. They could have started it off at the bottom piece, if you like. They could have started off like this, all right? They could have started off one that looks like this, right? Once again, we have started at 90 degrees, 180, 270, 360, and back to 90 degrees again, right? This is a DC, which means it's given us a, hang on, let's look. We've got, it generates DC, so it must be a commutator, and it's split, all right? Straightforward. All right. In the next one, we're going to be talking about a motor, okay, where the motor changes and, or rather we put a current through it and then we get a force on it. So I'm going to leave this one at this point, and the next one is going to be a motor. I hope we can get that one out the way very quickly, and then we can get our physics onto the last bit, which is transformers. So let's have a look at motors. See you in the next one. Cheers.